In this videotape, we will study relations and functions. I'd like to start by giving you a formal definition of a relation. Definition: a relation is any set of ordered pairs Now we're talking about basically ordered pairs of real numbers. We could have, for example, something like x comma y being a typical ordered pair. Now the set, of these ordered pairs, that is your relation. If you were to consider the set of the first elements, of all ordered pairs in the relation, this would be the domain of the relation, the set of the first members or first elements or first coordinates of the ordered pairs. Domain of a relation. This is the set of all first coordinates of these ordered pairs. And the range of the relation is the set of all second members or second coordinates of the ordered pairs in the relation. The set of all second coordinates. Let me give you some examples. Now, there are various ways to specify a relation. The easiest way would, of course, just to list the ordered pairs that are in the relation. For example, list the ordered pairs. We could have the following relation. The set consisting of the following ordered pairs: 2, 1, 3, 2, and 3, 4. This is a relation, and we've just simply listing the ordered pairs in the relation. These are, in this case, this relation consists of just these 3 ordered pairs. Another way of specifying a relation is to give an equation, which would yield the ordered pairs of the relation. For example, something like y equals 3x minus 1. If you let x comma y be a typical ordered pair in the relation, we'd talk about the set of all ordered pairs x comma y, where the y coordinate, the second coordinate, is 3 times the first coordinate minus 1. Now you can generate ordered pairs for this relation. You can make a little table of values. For example, you could let x be 0, and if x is equal to 0, then the corresponding y value would be 3 times 0 minus 1, or minus 1. We could let x equal 1. You get 3 times 1 minus 1. 3 minus 1, y would be equal to 2. You could let x equal 2. You get 6 minus 1. 3 times 2, 6 minus 1, y would be 5. You could substitute, of course, negative values for x as well in this case. Minus 1, if you substitute that for x, you would get minus 1 times 3. That's minus 3 minus 1 for minus 4. You substitute in minus 2. You get 3 times minus 2. That's minus 6. Minus 1, the y value would be minus 7. And of course, this could continue. Here I've listed 1, 2, 3, 5 ordered pairs in this relation. There are infinitely many ordered pairs in this relation. We could let x equal 1/2, 1 1/3, anything you wanted in this particular instance. A third way to represent a relation is to sketch the graph of the relation. We could have something like this. Here are x-axis and our y-axis, a rectangular coordinate system. And I could write, let's say here's the point 0, 2, and here's the point 2, 0. And we could say that this is a sketch of the graph of a particular relation. Now, In this particular case, it's a straight line, and one could, of course, determine the equation of the straight line. If you couldn't get the actual equation of the relation, then you would just be, you'd have to estimate to get various ordered pairs. Right? The 0, 2, and the 2, 0 you can see, but let's say you did not know how to get the equation of the line. Then you'd have to sort of guess what this point would be or any of the others. Okay, but very often, of course, we can actually derive the equation, and then you can generate as many ordered pairs as you want. So here are a variety of ways of designating a relation. Now, certain relations have an additional property. For certain relations, it is true that no two distinct ordered pairs have the same first coordinate. Okay, this particular relation violates this. Here are two distinct ordered pairs, and they have the same first coordinate. Okay, so this would not have this additional property that I'm talking about. But if you had a relation for which no two distinct ordered pairs had the same first coordinate, this type of relation would be called a function. Let me write down the definition of function for you. Don't worry if you don't understand it yet. You will in a few moments. Okay. Here we have definition of a relation. Now, a function is a relation in which no two different ordered pairs have the same first coordinate. A function is a relation in which no two different ordered pairs have the same first coordinates. Now, as I mentioned, this is a relation which is not a function. We have two different ordered pairs, 3, 2, and 3, 4, that have the same first coordinate, namely 3. I guess you could think of, say, well, if you think of the first coordinate as being an x value and the second coordinate as being a y value, okay? And you could think of this as sort of an assignment. In other words, 2, 1 means that the x value of 2 is assigned to the y value of 1. And it would be a function if, for every x, there was one and only one y value assigned to it. Okay? You could also think of the x values, these could be, say, students, and y values could be classes, classrooms that they're assigned to. Now, you would not want to have, for example, one student assigned to two different classrooms at the same time. In other words, student number 3, you don't want him to go to classroom 2 and classroom 4. But it's perfectly okay. You could still have a function if you had something like this. 2, 1, 3, 2, and 4, 2. It doesn't bother me here that you have two different ordered pairs that have the same second coordinate. That's perfectly okay. Student 2 is sent to classroom 1, student 3 is sent to classroom 2, and student 4 is also sent to classroom 2. That's okay. You do not want to have one student sent to more than one classroom. Okay. Every x is to be associated with one and only one y value. Okay, but a y value could have more than one x value associated with it. Okay, so here we have a relation that is not a function, and here is a relation that is a function. Not a function, is a function. Now, assuming we could sketch the graph of a relation, we have a geometric test that we can use to determine whether or not the relation is actually a function. Okay, let me sketch for you graphs of several relations. X coordinate, the x-axis in each case, y. Okay, here is a sketch of the graph of a relation. Here is another. Another. Okay, now, if to be a function has to be true that for every x there is one and only one y value assigned to it, well, picking an x value is sort of like picking a vertical line. If it is true that for every x there is one and only one y value assigned for it to be a function, then it would have to be true that no vertical line could cross the graph of the relation in more than one spot if that relation is to be a function. For example, over here we have the graph of a function. No vertical line crosses the graph of this relation at more than one point. So this is a function. We call this the vertical line test. What we're doing basically is like picking an x. When you pick a for example, this could be like the line x equals 1, this vertical line. If this vertical line were to cross the graph in more than one spot, that would mean for that x value there were two y values assigned to it. Okay, like over here. Here, a vertical line does cross the graph in more than one spot. That would mean for, let's say this is x equals 2. That would mean for x equals 2 there were two different y values assigned for it. Okay, so this is a function, this is not a function, using this vertical line test. Okay, let's try up here. Over here, we do have a vertical line which crosses the graph in more than one spot. It doesn't matter that you might be able to draw another vertical line that crosses it in only one spot. As long as there is one vertical line that crosses it in more than one spot, it is not a function. Not a function. Okay, over here, this is the graph of a function since every vertical line. Well, no vertical line crosses it more than once. In this case, every vertical line crosses it exactly once. Okay, so what we've been using is the vertical line test. Let me jot it down for you so you'll have it in your notes. The vertical line test is used to determine whether a given graph represents a function. If no vertical line crosses the graph at in more than one point, at more than one point, then the graph represents a function. The vertical line test is used to determine whether a given graph represents a function. If no vertical line crosses the graph at more than one point, then the graph represents a function. Remember, picking a vertical line is like picking an x value. And if it were to cross the graph in more than one spot, that would mean for that x there was more than one y value assigned to it. Remember, for a relation to be a function, it has to be true that every x is assigned to one and only one y value. And the definition for domain of a relation and function hold true for a function as well. In other words, the set of all first coordinates of the function would be the domain of the function. The set of all second coordinates would be the range of the function. Okay, what I want to do now is give you a variety of examples, and in each one we're going to try to determine, I'm going to give you equations, determine whether we have the equation which would generate a function, or if it's just a relation that's not a function, and to find the domain and the range of each of these. Okay, for our first example, how about the relation generated by this equation, y equals x plus 4? Okay, what we're going to do, whenever possible, we're going to try to sketch the graph of the relation and then apply the vertical line test. Okay, well, from the previous videotapes, we are aware that this is the graph of a straight line, and all we need is 2 points to 2 points determine a straight line. That's all we need to sketch it. For example, if x is equal to 0, y is equal to 4. If x is equal to 1, y is equal to 5. Okay, and we have something like that. We see clearly that this is the graph of a function. No vertical line crosses its graph in more than one spot. Now, as far as the domain and the range of this function, we can indicate the domain by D and the range by R. Remember, these will be sets. Okay? The domain is a certain set of numbers. The range is a certain set of numbers. Okay, now if it's not specified, basically what I'm talking about when I'm talking about the domain of this function is the set of all x values that you could substitute into this function and have it make sense. Because we would not want to have any division by 0 or any square root of a negative number. All the domain here, okay, unless you see something which is explicitly stated, for example, we could have something written down like this and it says all x greater than or equal to 5 only, then that would be the domain of the function. Okay, but if you're not given an explicit domain and you're asked to find a domain, the domain is basically as large, we try to make it as large as possible. All x values that you could substitute in and have this make sense. Well, in this case, since we have no fraction, we don't have to worry about division by 0, we don't have any square root, we don't have to worry about the square root of a negative number. Basically, the domain is the set of all real numbers in this instance. And similarly, in this case, well, we can see it from the sketch. If you substitute in the x values, what y values come out? Now, just let's look at this straight line. It really continues in this direction, continues upwards. We can substitute in any x value. What y values come out? Okay, well, you can get y values as small as you want by continuing this way. By choosing a suitably small x value, you can get a smaller y value as you'd like. You get all the y values continuing on upwards. So the range would be also the set of all real numbers. In general, I would recommend, say, finding the domain before you sketch it. In other words, ask yourself, are there any x values that you could not substitute in here? Okay, if not, the domain would be the set of all real numbers. If there were certain restrictions, okay, you would work with that. Or you could do it from the picture and see which x values have y values associated with them. And having made the picture, then you would want to determine the range, to see which y values were covered. Okay, instead of y equals x plus 4, let's try y equals x squared minus 4. Okay, the domain of this relation, at the moment we don't know if it's a function or a relation, the domain is once again the set of all real numbers. There is no fraction to worry about, no division by 0, no square roots of negative numbers to worry about. So basically, any x value that you would care to substitute in, okay, you could do so and get a y value to be associated with it. Now, as far as the range, let's first try to sketch the graph of this relation. Well, from earlier videotapes, if you recognize the first example as this being the equation of a straight line, you might recognize this as being the equation of a parabola. By the way, if this is totally foreign to you, I would suggest you go back and look at the videotapes in which we study sketching graphs of straight lines, parabolas, and other conics. All right. If this is a parabola, let's see, when x equals 0, y equals minus 4. That is the vertex in this case. Also the y-intercept. When y equals 0, to get the x-intercept, when y equals 0, x squared equals 4, x is equal to plus and minus 2. This is a parabola which is opening upwards. Continues, of course, and it's widening. Continues in this direction, up like that. The domain is a set of all real numbers. It may look a little deceptive. You may think, well, gee, it looks like it's stopping here, but it's not really. In other words, it's widening, okay, as you move out. If, for example, x were equal to minus 5, the y value would be minus 5 squared, 25 minus 4. Okay, 21. It would be rather high up already. Okay, but you can substitute in any x value and get a y value. Now we do, from this picture, we are able to determine the range of this relation. And the range is not the set of all real numbers. What y values do we get out? Okay, we never get y values that are any lower than minus 4. We get minus 4 when we substitute in x equals 0. Okay, well, we never get any y values beneath that. That is the lowest point on the graph of the parabola, 0, minus 4. So the range would be the set of all y values such that y is greater than or equal to minus 4. By the way, applying the vertical line test, this is, in fact, the graph of a function. This relation is a function. Vertical lines. Okay. No vertical line cuts the graph in more than one point. Okay, so this is a function. And we have its domain and its range. By the way, the first example also. It was a function, and we have its domain and range. Y squared is equal to x minus 4. Okay. Now, when you're looking for the domain, okay, it might be a little confusing. You might say, well, gee, there is no division, no fraction to worry about, and there are no square roots, but you'd be jumping the gun. This is y squared. If you were to solve the other way, y is equal to plus or minus the square root of x minus 4. So actually, to find a y value, you have to take a square root. So there is a square root involved here. We cannot take the square root of a negative number. Another way of looking at it is, well, y squared can't be negative, and therefore x minus 4 can't be negative. In other words, x minus 4 must be greater than or equal to 0. X must be greater than or equal to 4. You don't actually have to take the square root here. This spells it out for you a little clearer, that what's under the square root cannot be negative, namely x minus 4 must be greater than or equal to 0. But even without doing that, you see that the left side here is always greater than or equal to 0. Remember, the other ones were all y equals. This one is y squared. The left side, therefore, cannot be negative. Therefore, the right side cannot be negative. X minus 4 must be either 0 or positive, in which case x must be greater than or equal to 4. So the domain in this case is a set of all x values greater than or equal to 4. Okay, now what does this look like? Okay, now what does this look like? This is also a parabola. Okay, remember the first example, this was the graph of a straight line. Okay, we had an equation of this form. Neither x nor y appear to the second power. Okay, x and y were both to the first power. Now, if either x or y is squared, but not both, then we have a parabola. See, in this example, x was squared, but not y. It was a parabola. And in this third example, y is squared, but not x. We once again have a parabola. Okay, let's sketch the graph of this parabola. And as I mentioned earlier, these curves are sketched in much greater detail in earlier videotapes. Okay, if you try to get the intercepts, to try to let x equal 0, you'd see that y squared would be minus 4. You could not solve for y. This curve, therefore, has no y-intercept. If you let y equal 0, you would get that x equals 4. X equals 4 is the x-intercept. There is no y-intercept. It's a parabola. It can't be opening this way, because then it would have y-intercepts. It must actually be opening the other way. And of course, you could get some more points. For example, if x is equal to 5, y squared would be 1, y would be equal to plus 1 and minus 1. There would be 2 other points. And you could continue making a table of value to sketch the graph of this parabola. But remember, if it has an x-intercept here and it does not have any y-intercepts, the parabola could not be opening in this direction, because that would give it 2 y-intercepts. It must be opening that way. The domain, all x values greater than or equal to 4. And if you wanted to sketch it first and get this information from the sketch, well, that's fine. The range. Okay, now what y values come out? Well, remember, this is continuing to rise. And this is continuing to fall here. And basically, all y, if you go out far enough, all y values, okay, can be attained. So the range is the set of all real numbers. Now the question, is it the graph of a function? Is this a function? And the answer, of course, is no. Vertical lines, which certainly cuts the graph in more than one point. So it is a relation. It is not a function. Now, if you do decide to go on in mathematics, you will be studying functions a great deal. And this might not seem fair that a parabola that looks this way is a function and this one is not. Sometimes we want to be able to talk about a function and we're talking about a parabola like this. What we do is we isolate either the top half of this parabola or the bottom half of the parabola. The top half by itself would be the graph of a function. The bottom half by itself would also be the graph of a function. Although this is not the graph of a function, it is the graph. It is the. You could consider it as taking 2 different functions and combining their graphs. Okay, let me give you an example of that. Let's consider only a part of it. Say you were given y equals the square root of x minus 4. The positive square root. If I wanted the negative square root, I'd have to specify it with a minus in front. If you see nothing, that means the positive square root. Okay, now clearly, the domain of this function is a set of all x values such that x is greater than or equal to 4. We've seen this earlier. It's basically starting off the same as the other one. X minus 4 has to be greater than or equal to 0, because you cannot take the square root of a negative number. So x has to be greater than or equal to 4. Now, if I'm faced with the problem of sketching the graph of something like that, anytime it has a square root, the best thing to do is start off by squaring both sides. Okay, if you square both sides, we get y squared as x minus 4, which is the example that we just completed, the entire parabola. But the idea is to use this as a guide in sketching. In other words, you recognize it as a parabola, and then at the end to say, well, which part of the parabola, the positive square root, y is therefore never negative. So it's only going to be the top half of the parabola. On the other hand, if this had been the negative square root, y would never be positive, it would be the bottom half of the parabola. Okay, so you would use this to sketch the graph of the parabola, something like this. And then you'd say, but I only want the top half. Okay. And it would look something like that. This is just, in other words, to help you sketch it. This is the graph of y equals the square root of x minus 4. Now, the domain is all x values greater than or equal to 4. The range in this case is not the set of all real numbers the way we had in example 3, but in this case, y could never be negative, so it's a set of all y values greater than or equal to 0. Y could be 0 or higher. You never get a negative y value. Y is the positive square root. And this is a function. No vertical line cuts the graph in more than one spot. Okay, so if we have to, say, deal with a parabola that's opening right or left, and we want to consider the idea of a function, it is possible to isolate either the top half or the bottom half, whichever is necessary. Okay, let's do another example. X squared plus y squared equals 4. Okay, for the first time, both x and y are squared. It's not going to be a straight line or a parabola here. We are, in this case, this could either be a circle, an ellipse, hyperbola, and of course this is a circle since the coefficients of x squared and y squared are the same. And it's very easy to sketch the graph here. It's a circle with center at the origin and radius 2. Well, it's supposed to be anyway. Something like that. Okay, now you could get the domain by actually trying, in other words, to solve for y. Y would be plus or minus the square root of 4 minus x squared, or you could get it from the picture here, the domain and the range. In this case, when the pictures become a little more complicated, I guess it's a little easier just to get it from the picture. The domain would be the set of all x values between minus 2 and plus 2. And the range would be the set of all y values, also between minus 2 and plus 2. What y values come out? Only those from minus 2 up to plus 2. And as I said, if you wanted to work it this way to figure out if there's any restriction on x, you realize that there is basically a square root involved here. Which x values can be substituted in? Only those for which 4 minus x squared would be greater than or equal to 0, because otherwise you'd be taking the square root of a negative number. So it is possible to get the domain directly in this fashion without first having the sketch. For example, we see that we could not substitute in x equals 3, because we would get 4 minus 9, the square root of a negative number, and that wouldn't make any sense. Okay, or from the picture, we are restricted that x be between minus 2 and 2. And finally, this is not the graph of a function, because here we have a vertical line. And it cuts the graph in more than one spot. So this is not a function. The preceding example, of course, was a function. As our next example, let's consider y equals the negative square root of 4 minus x squared. All right, now, once again, when you have an equation involving a square root like this, I find it convenient to first square both sides to get a feeling for what kind of curve it is. Okay, now be careful when you're squaring both sides. y. When you square that, you get y squared. When you square the right-hand side, minus this times itself. The minus times the minus comes out a plus, and you'll get just what's under the radical. Some people feel that somehow the minus should stay. If it was, for example, y equals minus the square root of 7, okay, I think everybody would agree that if what is y squared? Y squared would be minus the square root of 7 times minus the square root of 7. The minus times the minus would be a plus. The square root of 7 times the square root of 7 would just be 7. Okay, so y squared would be simply what is under this radical. The minus sign would not stay. The same thing here. Y squared is simply what is under the radical. The minus sign doesn't stay. It doesn't get distributed through the parentheses or anything else. Okay, now in this form, well, we see if we add x squared to both sides, we are once again talking about our circle, the one that we just sketched before. This is the equation of a circle with center at the origin and radius 2. I thought that would help, but it doesn't. Center at the origin, radius 2. Now that's the graph of this equation. But remember, we're talking about y equals the negative square root. Y is therefore never positive. So we are talking about the bottom half only of the circle. So right over here we have sketched the graph of y equals the negative square root of 4 minus x squared. If it had been the positive square root, or if we saw no sign here, that meant the positive square root, that would be the top half of the circle. But here it's the bottom half. The domain and the range. The domain, just like before, is a set of all x values between minus 2 and plus 2. The range, however, instead of going from minus 2 to plus 2 as well, y can never be positive. It only goes from minus 2 up till 0. What y values come out? Minus 2 up to 0. So all y values between minus 2 and 0. And while the entire circle, this did not represent the function, since vertical lines cut it in more than one spot, the lower half of the circle, or the upper half of the circle, if we were going to consider that, does represent the graph of a function. Here we have a vertical line. No vertical line cuts it in more than one spot. So it is a function. Okay, for our last example, I will do the following. 4x squared plus 9y squared equals 36. Once again, x and y are both squared, but now the coefficients of x squared and y squared are not the same. They do, however, have the same sign, and we are talking about an ellipse. Once I know it's an ellipse, and as I said, if you're not sure of that, you can look at some of the earlier videotapes. Intercepts can give us pretty much the entire picture here. If we set y equal to 0 to solve for the x-intercepts, we would have 4x squared equals 36. If y equals 0, 4x squared would be 36, x squared would be 9, and we'd have x-intercepts of plus and minus 3. To find the y-intercepts, we would set x equal to 0. We would get 9y squared equals 36. Y squared is 4. Y is plus or minus 2. We have two y-intercepts, plus 2 and minus 2. And we will draw our ellipse. Just going smoothly through these 4 intercepts, or try to do that at least. All right. This is not the graph of a function, since vertical lines obviously do cut the graph in more than one point. And let's find the domain and range of this relation. The domain, which x values can be substituted in, anything from -3 to +3. And what y values come out, anything from -2 up to +2. And that brings us to the end of this tape.